Good morning, everybody. Welcome to physics. Just wanted to point out these notes here I have are all going to be things that we talk about in the next couple days. And there are also some sample problems and some explanations for some of the formula or the formulae. And these are all going to be on Moodle here, probably in the next hour. So you can look at this, you can download these, you can refer to them. I'm going to go through this a little bit fast because we only have 4 days left. So if you want some better understanding, when we, like we do when we have a little bit more time, I encourage you to look at these notes. So these will all be on Moodle, and you can see right up here, they're called Energy, Work, and Power Notes. So I just want to point that out. And if we take a look at yesterday's lab, we can see that, oops. So if we take a look at yesterday's lab, I got a student lab from before. This is the velocity graph. And the part that you guys graphed most likely was, just this part right here. And you notice that here's your 0 point. So the actual graph line is right here. You can see right there when the velocity is 0 is at the top of the throw. Many of you guys probably had that right. I don't know though if you had this part right, because when the ball came back down, then it was in the negative direction. Maybe it did, maybe it didn't. But if we look at the other part of this, here's the kinetic energy and the potential energy parts. I know there was a mess up with one of the computers, but I think we figured that out. I don't know why it was doing that, but you can see they're completely opposite of each other. So that should tell you that they're changing from one form to the next. So if you look at this line here, this would be the kinetic energy, right? Because it's the highest. And right when you start that throw, you're going to have the highest velocity. And kinetic energy, which you should know from physical science, is the energy of motion. So you have the biggest change in displacement in the beginning, so you have the highest velocity, therefore the highest kinetic energy. And then it'll get less and less and less and less in a parabola form. And then right down here is our lowest kinetic energy, and that's a 0 point. So that's going to be at the top of the throw when there's 0 velocity. Does that make sense? But at the same time, what did you see happening? You saw that you have this potential energy getting bigger and bigger and bigger. So this is an introductory lab. If you remember potential energy from physical science, it's the positional energy, or a potential to have, or potential to do work, or potential to have kinetic energy if released. We got a question here. The question is, how can it have potential and kinetic energy? And if you look here at this point, it doesn't have kinetic. It has only potential, right?
But right before that.
Right before that, it has some, right? So through our discussion, that'll be one of the first questions I answer today. I guess I might as well answer it now. But if you just think of, you're out on the playground, you got a swing, right? And that swing, as long as these ropes don't break, that swing is not going to get any lower. So that would be a 0 point for your potential energy, because it can't fall any further, okay? But if the swing, or when the swing starts to loop up in this position later, okay, that will have, if I pull the swing up to this point and let it go, then it would have a potential to move. Does that make sense? So if this is the highest point, this would be the biggest potential that you'll get. Now, right as it gets to that height and turns around, what's the velocity going to be? 0. So at this point, the kinetic energy is 0 because there's no movement for that instant. Potential energy is the max it can be. But then what happens right here in the middle is the question. Because we know it's moving. I didn't draw that very well. We know it's moving, so it has a velocity, and so it has kinetic energy. So maybe at that point it might have half kinetic, but then it also has a potential to fall further, right? So it has half kinetic energy and half potential energy. Does that answer your question? Okay, that's a good question. So, and if we look at these graphs, you can see that there's an exact exchange. So it's a one-to-one exchange. As I increase my kinetic energy, which would be, increasing would be on the way down. So this looks like it's going up, I guess, on the graph, but in reality, that's when the ball's coming back down. And as I increase my kinetic energy, what do we notice is happening with my potential? My potential here is decreasing. And for every increment of change in kinetic, you have the exact same magnitude of incremental change in potential because they're interchanging. So the whole idea of this then is the conservation of energy. So you've always heard of the conservation of energy, conservation of mass, or now they're kind of saying conservation of mass energy, because they're interchangeable. But in this case, we're not talking about any conservation of energy and mass, or I mean any change of energy to mass or vice versa. We're only talking about the change in energies. Okay, so with that, on that note, we'll look at the next piece. The next graph then was, oh, it's not on here. What would the next graph be? Total energy. So if I had total energy and time, what would that look like? It's a straight line right across the map or the graph. Total energy. Because total energy, when we're talking mechanical energy is potential and kinetic. So energy total would be potential plus kinetic. And the energy total, if it is completely conserved, this will be completely interchangeable. So if I lose kinetic, it turns into potential. And you can see with, I throw this up, losing kinetic, potential, back down to kinetic. Or if you have a swing out on the playground, potential, kinetic, potential, kinetic, potential, kinetic, potential. So kinetic max is always at the bottom. Potential is 0. And then potential max is at the top. Kinetic is 0. And whatever that energy is, let's just give it a number, 100 joules. Let's say here I have 25 joules of potential. How many do I have of kinetic? 75, right? Because 100 joules is my total energy. Any questions about these numbers? Okay, this is stuff you went over, 3 years ago in physical science. Now there is a problem here though. when you're out on the playground, you don't just hear, or you don't just see the swing moving, you hear it, right? It's, oh, that's sound energy. And that comes from the vibrating of the particles of the metal. That's what that sound comes from. Well, that's movement. So if I just smack the board, see that? I'm actually hitting those particles that make up the board. And those particles are moving faster than they were before. They're moving in straight lines. The problem is we got particles all over the place. Like, it's really unimaginable how many particles we have that make up this board. And if I hit this board, well, this one's going to go in a straight line until it hits something else, and it's going to bounce off and go in another straight line. This is going to go in a straight line until it hits something and bounce off. And for a solid, they don't really move anywhere. They just jiggle in place. But that movement of all these particles numbered by something we can't even imagine because it's so big is completely random or all directions at all times. And that's called heat energy. Or another word for that is thermal energy. Heat and thermal energy are not conservative. Okay, so heat and thermal are what we call non-conservative, where mechanical energy is conservative, which means that energy is conserved, transforming from kinetic to potential, potential to kinetic. Heat and thermal, though, doesn't transform back into kinetic. Because what happens is these particles hit these particles, those particles hit those particles, and before you know it, this heat is spread out and dispersed throughout the whole universe, and it's undetectable, almost. Although there's microwave, radiation and things might be caused by that. I'm not sure. So, what do you think would be a non-conservative? Well, here, let's have a question here first. What's the question? What do you think would be a non-conservative force or a non-conservative energy that we've already been talking about and dealing with in the last chapter? Any ideas? Well, take your hands, rub them together. What do you get? Friction, which causes increase in heat or thermal energy. And you can measure that by temperature. So, then we would say friction is this go-between. A friction force is a go-between that takes away from mechanical energy and adds to this thermal or heat energy. So this is definitely non-conservative. Okay? Keep that in mind. So let's talk about kinetic energy. Simplest form, or what is kinetic energy? What do you guys remember? It's the energy of motion. Very good. So let's talk about motion, kinetic energy. Let's say that I throw a ball at 5 meters per second, and you try to catch it. I throw a ball at 10 meters per second, you try to catch it. Which one's going to have more energy or take more energy to catch? 10, right? That makes sense. You've all encountered that in your life, right? That was the next point, yeah, but this is the same ball. Okay, so the only difference is the velocity. So we can say that kinetic energy then is directly related to velocity. Easy by our life experience, right? What if I throw a bowling ball at you versus a baseball? Both at 5 meters per second. The bowling ball hurts quite a bit more, right? Or it takes more energy to stop. I meant to say bowling ball. I have to listen to that on the recording and see what I did say. So, it's also related to mass, right? Okay, now in those notes I was showing you, there's a lot more to this understanding, but we can at least from this, and this is what we have time for today, know that our formula has something to do with M and V, and energy being directly related to that, right? As mass goes up, energy goes up. As velocity goes up, energy goes up. This is the rest of the formula. It's 1/2, and this V is squared. So that V being squared gives it more power than just a regular V, right? Okay. So the whole question about who gets to play football on Friday, Saturday, and Sunday. It used to be said that the people with more mass get to play on Sunday. If you have more mass, you go all the way. But we also have to realize that if you have more speed, you get to play on Sunday too. In fact, the speed component of this is more powerful than the mass. Now the change in the speed is going to be less for the Friday, Saturday, Sunday football players versus the mass, but definitely have to take into consideration the velocity too. So it's high school, college, and pro football, right? That's what we're talking about? Oh yeah. So that's kinetic energy. And then we have, today we're going to talk about potential energy due to gravity. Okay. Okay, so this is potential due to gravity. There is more than one kind of potential. We're going to talk about spring potential energy, which would be dart guns and bungee cords and things like that. We're not going to talk about chemical energy really besides today, but E equals mc squared, that's mechanical, or that's chemical energy. But this potential energy subscript little g is due to gravity. So let me ask you, if I drop a ball from 1 meter high versus 5 meters high, which one is going to take more energy to stop? 5 meters, right? Sorry, didn't mean to cut you off there. So we can say that it's directly related to height. How about if I drop a bowling ball versus a baseball? Bowling ball, directly related to mass. How about if I drop a baseball on the moon versus a baseball on the earth? Which one's going to take more energy to stop? Earth, because the little g up there is like a sixth or something like that, right? Okay, there's less acceleration because there's less pull due to gravity. So we can say that it's directly related to G2. And this is a really easy formula because this is just straight out mgh. Okay, and all these energies and everything we talk about, energy, work, which we haven't talked about yet, is measured in joules after James Joules, or James Joule. Okay, so mgh. Makes sense, right? Okay, now, I gotta explain one more thing here for you today, just kind of simple. Let's say that I have a ramp, okay, and I have a V sub naught equals 0. And let's say that I have height change equal to 5 meters. Let's say that this is a 2 kilogram ball. Okay. And let's say over here I got the same thing, 2 kilogram ball. And it's going to go through a height change of 5 meters. My question is, what's the velocity here for that ball, and what's the velocity here for that ball? Any ideas? Okay, let me ask you this. Is the red one going to be less, equal to, or more than the green one? Okay, that's true. It's tough because it has to go through a further distance. Now, I do have to also say we're going to ignore rotational inertia. which would be, you know, kind of the energy wrapped up in moving this ball, like rotating it. We're going to ignore that. We're also going to ignore any friction. Okay, so thanks for all you voting participants. I do have to tell you that they're the same. They are the same. And the reason why is because there's the same change in potential energy for both of them. Now, like you said, what is there is a difference. This one's going to take longer to achieve that. And if you look at your forces, you know, because force causes a mass to accelerate, there's going to be a full 20 newtons of force on this guy. On here, it's going to be a sine theta 20, which is less than 20. So you can see right here, there's less of a force on the ball that's going to move it down the ramp. But once it finally gets down to the same change in potential energy, which we're not changing mass, we're not changing little g, we're just changing height. Once we get to that same change in potential energy, where else would the energy go? It's completely conserved. It has to go directly into kinetic energy. Now this takes longer, but it should be the same velocity. Okay. Now you could do it any way you want to. You can do it with the forces and acceleration. You can do it with kinematic problems. But I'll tell you right now, energy is easier than that.
So in the formula.
So if you look at these formulas, you'll say, hey, the potential that I have at the top is going to be fully realized into kinetic at the bottom. Now, I'll tell you, I haven't told you this yet, but energy has no direction. It's scalar. Okay? So if you look at this, mgh equals 1/2 mv squared. What do you see happening to these two formulae right now? Mass cancels out because it's the mass of the ball on both sides, right? So then our velocity here becomes the square root of 2gh. Does that look familiar to anybody? Yeah, because if you remember, way back when, we had this little formula called v squared equals v sub naught squared plus 2ax. This one had direction. But if you start with a 0 initial velocity, v equals the square root of 2ax. It's the same equation. Okay? So now you should always be thinking of this h as delta h, because it's a change in height, because, you know, height, where would you measure absolute height from? There's no place to measure absolute height, so it's always going to be a change in h. Hey, I got a question for you. Can you define work?
Yes.
Or, well, let's define energy first. Okay, let's define energy. Energy would be defined as the ability to cause change. So it's ability to cause change, or ability to do work. Okay? So this isn't like the everyday work. There's actual definition for work I'm going to talk about a little bit more. But I want to say right now, the simple definition of work, the easiest way to think about it is a change in energy. So if something is worked upon, then it gets its energy changed. Now it either gets changed to potential, changed to kinetic, or changed to thermal. So work is this kind of go-between word that we can use to describe the change in energy. So I got one more question for you. Let's say that I go like this. I go through a height change of 5 meters. I've got a mass that's 2 kilograms. Okay, and we'll just use 10 for gravity. And let's say that down here I end up with 90 joules of kinetic energy. Okay, does that add up? It doesn't add up, right? Because if you go MGH here, this would be a potential up here of 100 joules. You agree? I only have 90 joules down here. Ignoring rotational inertia, what happened? Something worked on it. Yeah, so friction is going to be forcing on this ball the whole way down, and that's going to do work. How much work did friction do? 10 joules of work. So, what energy did friction turn this mechanical energy into? Yeah, so that's going to mean this is an increase in thermal energy of the ball and the ramp. Okay, so that got a little lengthy, but hopefully that helps you with your next couple homework assignments. Have a good day.